So again, I want to welcome everyone to tonight's webinar on global weather patterns. I'm Joe Delicarpini, the Science and Operations Officer at the National Weather Service, Boston Norton. And with me tonight, Rodney Chai, one of our meteorologists, and a new face, Rob Megnia, one of our meteorologists. Rob came to us last year from the Lake Charles, Louisiana forecast office. Rob, I believe, just before the hurricane hit, literally, I think it was a week before. But Rob is a native of Marshfield, so he's back home here in southern New England, and we're glad to have him aboard. Rob and Rodney are kind of our local experts on global weather patterns. So Rob put a lot of this material together along with Rodney. So guys, thank you so much for helping out tonight with this. So I'm going to hand it over. I believe, Rob, I think you're getting started. So I will hand it over to you.
All right, great. Thanks, Joe. Just a quick sound check.
Yep, you sound good, Rob. Sound good, Rob.
Awesome. All right, so global weather patterns. Well, before we dive into the different global weather patterns, I wanted to show everyone this model that kind of describes the general circulation that we see around the globe. And this is just referred to as the three-cell model. So maybe in past webinars, when you hear us talking about getting ready to forecast, we use this approach called the forecast funnel, which is basically the process of understanding what's going on the broader, larger scale before we start making a forecast for home or on the local scale. So the top of the forecast funnel starts right here with the global circulation. And this three-cell model is broken down into three components or circulations or cells. So the first cell that you see in the center of the diagram is the Hadley cell. And this is characterized by the convergence of the northeast and southeast trade winds at the equator in the low latitudes. And when they converge, they rise. And as they reach the top of the atmosphere, they spread out to the subtropics where they then sink back to the surface. So this persistent convergence along the equator is sometimes referred to as the ITCZ, which stands for the Intertropical Convergence Zone. And it's here where you get a lot of those tropical showers and thunderstorms. And it's for that reason along these low latitudes is where you'll find most of the planet's rainforests. And then also where you have that sinking air in the subtropics, sinking air tends to suppress precipitation. So these latitudes tend to be drier. And it's in these areas of the planet where you'll actually find most of the Earth's deserts. So a lot of that can be explained by the Hadley cell and the general circulation that it provides. So moving poleward into the mid-latitudes, which is where we live, we have the Ferrel cell. So the Ferrel cell is characterized by the mid-latitude westerlies, where air flows poleward and eastward near the surface of the Earth, and it actually flows equatorward and westward at very high altitudes above the jet stream. And it's the Ferrel cell that kind of governs the west to east flow we see with our storm systems over the United States. And then finally at the top, we have the third cell, which is the polar cell, which is characterized by cold sinking air at the polar latitudes that eventually come to the surface and become the polar easterlies. And then sometimes you have convergence of the polar easterlies and the mid-latitude westerlies in the subpolar latitudes of the planet. And it's in this region where you'll tend to find what we call the subpolar pressure systems. So this is just a gross generalization of how the planet flows. And there are often deviations and anomalies that frequently occur in these circulations. And those are the global weather patterns that we're going to be talking about here today. Next slide. So another name for a global weather pattern is a teleconnection. So a teleconnection is simply defined as a statistical relationship between atmospheric variables that exists over very long distances. So on the last slide, I discussed the anomalies and the deviations that inevitably occur in that three-cell model of the general global circulation. Well, the most notable anomalies that we detect can sometimes be referred to as leading modes of low-frequency natural variability. And there's actually some fancy math and statistics that scientists have used in the past to determine where these modes of natural variability occur within the larger scale circulations. And this is important because by recognizing when these variations are going to occur, we can get some clues on what kind of weather to expect, especially with respect to behavior in the jet stream. And as we know, the jet stream is critical to forecasting in the mid-latitudes because it tends to be the divider between colder and warmer air. And the jet stream is often responsible for producing many of the mid-latitude storm systems that we see in the United States. Next slide. So these teleconnections have names associated with them. Some of them you may have heard before. I'm sure most people have heard of El Nino and maybe La Nina. And these teleconnections describe variations in the large-scale flow in both the mid to high latitudes and in the tropics. So in the mid to high latitudes, we have the Arctic oscillation, the North Atlantic oscillation, the Pacific North American pattern, the Eastern Pacific oscillation. And then in the tropics, we have, of course, El Nino and La Nina, which is probably the teleconnections that are most known by the public. And we have another one called the Madden-Julian oscillation. And all of these can play a role in having an impact on the large-scale flow on the planet and can even impact weather all the way up here in New England. And we're going to go over each of these patterns today and talk about how they can affect weather locally. So we'll start with El Nino, or the El Nino Southern Oscillation, which is sometimes known as ENSO. And El Nino refers to sea surface temperature anomalies over the equatorial Pacific off the west coast of South America. So specifically, when the sea surface temperatures in this area are warmer than normal, as seen in the bottom image, we call this an El Nino event. But when they happen to be colder than normal, like in the top image, this is called a La Nina event. And if temperatures are right around normal for what we're expecting, that is simply just called ENSO neutral conditions. Next slide. Okay, so you might be wondering, I thought we were here to talk about atmospheric circulations and not sea surface temperatures. Well, in the case of El Nino, we're talking about both. And that's because these sea surface temperature anomalies have an effect on the circulation over this region of the Pacific that's known as the Walker circulation. So under normal conditions, the Walker circulation is driven by the easterly trade winds that we talked about on the first slide, where winds push warmer ocean water at the ocean surface westwards. And as a result, colder water comes up from beneath through a process called Ekman upwelling. So this can be seen in the top diagram by the equatorial thermocline shown in the top image. So where the ocean temperatures are warmer to the west near the maritime continent and Australia, you tend to have stronger areas of low pressure that produce more rainy conditions. And then meanwhile, off the west coast of South America, where the sea surface temperatures are colder, there tends to be sinking air aloft that suppresses rainfall and produces high pressure. So under El Nino conditions, you have a weakening in the easterly trade winds. So this results in reduced Ekman upwelling, and then the thermocline flattens. So as a result, you have more rainfall over some of the eastern portions of the Pacific than you might see otherwise under normal conditions. And then in some cases, drier conditions over the maritime continent and Australia. And these conditions can actually have impacts on the jet stream as well, we're going to talk about in a minute here. So here's some of the global influence that El Nino can have on rainfall patterns across the globe. And you can see it's not just limited to the Pacific or the maritime continent and Australia. You can see, for example, in the United States, from January to April, if you're in an El Nino event, there tends to be wetter than normal conditions with drier than normal conditions in the Pacific Northwest and portions of the Midwest as well. And, it also can affect, rainy and drier conditions as far west as Asia and Africa as well. So El Nino can also have a pretty significant impact on tropical cyclone activity. Hold on a second here. So typically under El Nino conditions, this spells good news as far as tropical activity goes in the Atlantic, because it tends to have a suppressing effect on the amount of tropical cyclones that can spin up. So this is because during El Nino conditions, there tends to be increased vertical wind shear and greater atmospheric stability over the Atlantic basin. Now, this is important because for tropical cyclones, you want both low stability and weak vertical wind shear. And recall that vertical wind shear just refers to changes in wind speed and direction with height. And for warm core systems like tropical cyclones, too much wind shear can result in the storm becoming disorganized, causing it to tear apart. But then on the other side of Central America, over the Pacific, during El Nino events, you tend to have more instability and less vertical wind shear. So it's under El Nino conditions that the Eastern Pacific basin tends to have more tropical activity. So some of the local influence from El Nino, as we talked about. So during El Nino conditions, the jet stream tends to move a little bit further south over the United States, resulting in wetter and colder conditions across the southern tier of the United States, and generally drier conditions and warmer conditions for portions of the northeastern United States. And as far as the wintertime goes, El Nino winter times in New England are often associated with a higher frequency of freezing rain events and mixed precipitation events due to the warmer conditions. So now we'll talk about El Nino's counterpart, La Nina. So La Nina is essentially just the opposite of El Nino in almost every way. So rather than a weakening of the easterly trade winds that you see during El Nino, during La Nina, you actually have a strengthening of the easterly trade winds and the Walker circulation. So this results in enhanced Ekman upwelling and a steepened thermocline. So as a result, you tend to have stronger, higher pressure over the eastern Pacific, which suppresses convection and rainfall, and stronger, lower pressure over Australia and the maritime continent, which can result in enhanced convection and even more rainfall. So the global influence of La Nina, as you can see, this looks very similar to the last map we saw here, but essentially everything's flipped. Where conditions were wetter than normal, they're now drier than normal across portions of the southern United States and the Northeast. And of course, over the eastern portions of the Pacific is drier than normal, with the wetter areas being over the Australian maritime continent from the enhancement of the low pressure over that region. Yeah, and then locally, so with the higher pressure over the eastern Pacific, you have some blocking that can result in the polar jet stream diving into the central United States. And as for us up here in New England, we tend to have above average precipitation and colder than average temperatures. And that goes for much of the rest of the northern United States as well. And then for hurricane season, so during El Nino, that's good news for the Atlantic Basin, but not so much for La Nina. And we were actually in a La Nina this past hurricane season, which saw a record. I believe it was a record for a number of named storms that we had. So during La Nina, you tend to have more instability and less wind shear over the Atlantic Ocean, which, as we talked about before, enhances the conditions necessary for tropical cyclones to develop. And then again, the reverse effect on the other side of Central America, you tend to have the reverse effect where there's stronger wind shear and more stability. So tropical cyclones are suppressed in the Eastern Pacific under these conditions. So that pretty much wraps up El Nino and La Nina. And now I'm going to talk about another interesting teleconnection that is centered in the tropics. And it actually is related to El Nino and La Nina as well. And this is called the Madden-Julian oscillation. So these don't occur during El Nino events. Madden-Julian oscillation isn't active, so to speak. It's only active during ENSO neutral events or La Nina events. So what the MJO is, it's an eastward moving pulse of showers and thunderstorms near the equator that spins up over the over the Indian Ocean and moves eastward to the Western Pacific Ocean before fizzling out, and then just almost magically it pops back up in the Indian Ocean again. And this kind of cycle recurs every 30 to 60 days. And this moving pulse of showers and thunderstorms being followed and with suppressed convection, and suppressed convection out of head can tend to have impacts on weather across the globe and also in the United States. So unlike El Nino and La Nina, that's kind of measured by the sea surface temperature anomalies, the Madden-Julian oscillation, which again is that eastward moving pulse of showers and thunderstorms, it's measured in phases by where that moving pulse happens to be on its trip from the Indian Ocean to the Pacific Ocean. So it starts out in the early phases in the Indian Ocean, and as it starts to move eastward, you move into phases 3, 4, and 5 by the time it makes its way to the maritime continent, and then eventually 6, 7, and 8 as it starts to make its way from the Western Pacific over into the Central Pacific. So here's kind of a nice little animation that shows the average conditions associated with each of the MJO phases. And I'd say turn your attention to the right side of the image that actually shows the east coast of the United States. And you see as the Madden-Julian oscillation makes its way further into the Pacific, you start to see a strengthening of the Pacific jet stream and the jet stream across the eastern United States, which of course, as we know, can play a role in the storm systems that we see out here. So how exactly is this propagating pulse of convection way down in the West Pacific and the Indian Ocean impacting weather in the United States and New England? Well, when the MJO reaches the Pacific Ocean and it has all this moisture associated with it, that moisture plume has to go somewhere, right? So when it reaches the top of the atmosphere and kind of spreads northward to the poles, it can result in a splitting of the Pacific jet stream. So you can get stronger winds a little bit more equatorward, or new jet that forms, and it can transport that moisture from the equator and from the Madden-Julian oscillation all the way to the west coast of the United States. And this is how the west coast gets what's called atmospheric rivers, which is largely responsible for a lot of their precipitation. And as far as the east coast of the United States goes, anytime you have something that's messing with the jet stream, you're going to have impacts on potential storm tracks. So different phases of the Madden-Julian oscillation can result in different storm tracks across the United States. So locally, recently, a group of scientists did some research on how the different MJO phases can affect snowfall in a very specific area of the world that you might recognize on this map here. They wanted to see how the MJO affected snowfall in southeastern New England. So they happened to find some pretty good results that suggested that when the Madden-Julian oscillation is in phases 7 and 8, and that's kind of when it's located over the Pacific, there tends to be an increased probability of snowfall for locations along southeastern Massachusetts. And on the reverse side, there tended to be a decreased probability of snowfall in phases 4 and 5, which I think is when it's making its way from the maritime continent into the Pacific. So let's put that theory to the test, and we'll take a look back at one of the snowiest winters that we ever had here in southern New England, and that was back in 2014, 2015. And I'm sure Joe might know the exact number, but I know it was 90 plus inches of Boston in 30 days. So the plot on the right is used to kind of track where the Madden-Julian oscillation is. So as I mentioned, phases 7 and 8 is when it's located in the Pacific Ocean, and that blue line represents time. So that blue line is essentially from late January of 2015 to mid-February of 2015. And that timeline matches up with the graph that you can see in the bottom left-hand corner as well that shows the snowfall at Boston during that time period where we received over 90 inches of snow. And as you can see, the MJO was largely in phases 7 and 8 for the duration of that snow blitz that we saw, which matches up nicely with what was found in that research as well. So there might be something to be said about the MJO for New England winters. Now, how about last year when we had almost no snow, right? It was a very dry year last year in New England as far as snowfall goes. So on the right, again, this covers a much longer time period than the last slide, but this is the MJO phase from January 1st, 2020 to March 31st, 2020, but really just focused on the red line here, which is most of January and February, where the MJO spent a lot of its time in phases 4 and 5. It did make its way to 7 in late January, and I thought it was interesting too that almost the only snow on this graph right here occurred right around the time that MJO went into phase 7 briefly, but it obviously wasn't enough to get the storm tracks we needed to get any significant snowfall here in Boston last year. And then how about this year? This year was much snowier than last year, much closer to normal. And the Madden-Julian oscillation from kind of early January through mid-February actually spent a good amount of time in phase 7, and kind of on the line between phases 6 and 7. And where this line turns from purple to red is when we start getting into February, which is where we start to see a higher frequency of snowfall events this year. So, I think, at least with these 3 examples, seems to match up well, that phases 7 of 8 of the Madden-Julian oscillation can be favorable for more snowfall in the wintertime here in New England, where phases 4 and 5, not so much. So that's all I have on the tropical teleconnections for today. I'm now going to turn it over to my coworker Rodney here, who's going to discuss some of the mid-latitude teleconnections. And if anyone has any questions on the tropical ones, we can talk about that later. So, Rodney, the floor is yours.
Well, thank you so much, Rob, and thank you for your excellent discussion about the ENSO and MJO. And I know, it's a lot of teleconnections that we are covering tonight. So, like what Rob said, feel free to ask questions at the end of the presentation if you have any for us. So, let's take a look at the North Atlantic oscillation next. And the next 4 teleconnections, if you are confused, you can kind of infer their locations based on their name. So in this case, North Atlantic oscillation, not surprisingly, the feature is related to the North Atlantic Ocean. And in this case, we have the subtropical high pressure over Azores, which is about 1,000 miles west of Portugal, and then you have the subpolar low pressure kind of near Iceland. So how this low pressure and high pressure interact with each other, their relative strengths would determine whether the NAO is negative or positive. And some of you who may love winter weather, you would like the NAO to be negative. And in this case, this is what the graph is showing. You can see it going negative. And I believe this is actually a month ago. So that kind of coincided with a more wintry phase of our winter so far. And once again, the North Atlantic oscillation is the fluctuation in the sea level pressure between that subtropical high pressure and subpolar low pressure, and again, it's measured in positive and negative phases. So during a positive NAO phase, you have the strengthening of the subtropical high pressure over Azores, and this increased pressure gradient. Remember, pressure goes from winds flows from high pressure to low pressure. This supports a more west to east jet stream track. So in this case, because the jet stream is relatively flat, it kind of favors less storm systems for southern New England. And again, this the local influence would be fewer intrusions of the cold air into southeastern U.S. So in other words, it would be warmer over eastern U.S. So again, if you like snow, doesn't mean that it's a shutout, but it would take the odds against a snowier winter because you just don't have the colder air in place. And moving on to the negative NAO phase, in this case, the subpolar low pressure is relatively stronger because the subtropical high pressure near Azores is weaker. And when this happens, you favor a blocking over North Atlantic. And some of you may have heard the term Greenland block. So when you have a block downstream of New England, storms tend to move out slower. And in this case, you would have more residence time, and under the right conditions, you have more time for precipitation, and makes snowier storms more possible, especially when it coincides with more frequent intrusion of colder air from northern Canada into eastern US. And locally, again, it means cooler conditions for eastern US. So moving on to the Eastern Pacific Oscillation. And again, the word Eastern Pacific implies that we're talking about the Eastern Pacific Ocean. And there are a lot of similarities with NAO, but in this case, it's over the Eastern Pacific. So kind of focus, just west of the West Coast. And it can influence Pacific jet stream patterns and intrusion of Arctic air into the US as well. And again, it's measured in positive and negative phases. So in the positive EPO, in this case, it tends to favor, a greater influx of the milder Pacific air. So in this case, you kind of cut off the intrusion of the really cold northern Canadian air. In this case, and that's really because there's a low pressure system kind of just west of the West Coast. And in this case, this makes the jet stream flatter, and in turn, you tend to favor above normal temperatures across much of continental US. And on the flip side, the negative EPO, you have a semi-permanent high pressure off the west coast of the United States. And this leads to the bulging of the jet stream. And so this favors a deeper trough over much of the eastern US and allows the colder air to come in from Canada. The third teleconnection that I'm going to talk about is the Pacific North American pattern, otherwise known as the PNA. And again, it's measured in positive or negative phases. But what is different, how it's different from the EPO, the PNA and the NAO is that if you like snow, if you like, colder winter, you want the PNA to be positive. And I would talk about next slide, please. So the positive PNA phase, in this case, is associated with above average high anomalies over Hawaii and the Pacific Northwest, and on the other hand, below average high anomalies over the southeastern US. And so a positive PNA phase, you have a ridge over the northern Rockies and the western US, and a deep trough over the eastern US. And this amplified trough ridge pattern favors a cold, more frequent intrusions of colder air into eastern US. And locally, it supports cooler or wetter conditions for our area. And if you live on the west coast or western half of the US, you'll be in a warmer and drier pattern. And on the flip side, negative PNA phase, you have below average high anomalies over Hawaii and the Pacific Northwest, and above average high anomalies over the southeastern US. And this favors a deeper trough over the western half of the United States and a ridge over the eastern half of the U.S. And that basically kind of cuts out the intrusion of the colder air from Canada into eastern U.S. So again, locally, positive PNA phase, the trough over the western U.S. supports cooler and wetter conditions over there. And, so for us in eastern U.S., we would experience warmer and drier conditions. And let's talk about the Arctic oscillation. And basically, this is a pattern that looks at how the air near the Arctic Circle behaves, and this influences the north to south steering of the jet stream, and again, it's also measured in positive and negative phases. So in the positive AO phase, you have below average air pressure over the Arctic, and paired with high and average pressure over the northern Pacific and Atlantic Oceans. And what this means is that the jet stream would be further north than normal under these conditions, and the storms can usually be shifted northward than their usual path. So in a positive AO phase, don't be surprised to see that the storms tend to be steered towards Canada, and for us it will be kind of too far to the south, and locally that means a warmer and drier pattern. And again, in the positive AO phase, locally there's fewer colder air outbreak, and because the storm tracks are further north, it means fewer winter storms for us. And negative AO phase, so there's above average air pressure over the Arctic region and below average pressure over the northern Pacific and Atlantic Ocean. And because of this, the jet stream would shift further south towards the equator. And some of you may remember during the severe Arctic outbreak over the central part of the U.S. Just a few weeks ago, the AO was actually deeply negative, and snow and cold came all the way south towards southern Texas and even into Mexico because of this development. And that's because the jet stream came so far to the south. And when this happens, the mid-latitudes and in some rare occasions, the subtropics may even experience outbreaks of frigid polar air when the AO is deeply negative. And locally, it is associated with more frequent cold air outbreaks for the eastern U.S. and has been linked to a higher frequency of nor'easters. And right now, the AO is currently negative as of when we made the presentation. So right now, the AO is actually positive. But you may remember that during the first 2 weeks of February, in fact, into the third week as well, we had a pretty snowy pattern, and we were actually in a deeply negative AO phase, going into neutral and actually slightly positive. And when the AO goes from deeply negative towards neutral, research has shown that this is associated with higher frequency of winter storms over the eastern U.S. And so that was exactly what happened this winter. So right now, I'm going to pass it back to Joe, and we'll take questions.
All right. Thanks, Rodney, and thanks, Rob. Great presentation. Let's see. We'll start with some questions here before we get to our weather briefing. So from John, what forces give rise to the trade winds, westerlies and easterlies? I don't know if Rob, you want to take that? That was probably from your section.
Yeah. The simple answer to that is just the fact of the Earth being tilted on its axis. It's just the differential heating that occurs. So at the equator, where the most sunlight is received, you right tend to have the warmest temperatures. So that's where you're going to get the lowest pressure. So that's where air is going to gravitate to, is towards the from higher to lower pressure. So that's where I believe that the trade winds come from.
All right, and just a follow-up question. What is the period of a La Nina or El Nino event? Months or years? Is there a steady cadence or does it vary?
I don't know the exact answer to that, but I believe it's on the order of months. Joe or Rodney, if you have any more insight into that, please feel free to share. And I think there has been cases where it has lasted for years as well.
Yeah, I think, Rob, for the most part, it's on the order of months, maybe 4, 6, 8 months at a time. But yeah, it does vary where I think there's been some extreme, probably depends on the strength of it too, to come in and out of it. But for the most part, it's months, but I think there have been a few extreme cases where it's been on the order of a year or even a little bit longer than that. So good question. Okay, from Linda, are you seeing an effect from the reduction of ice in the Arctic? If so, how large?
I'll have to stay in my lane in that one. I guess I'm not really sure. I bet there are some climatologists out there who are doing some studies to see how, any changes in Arctic ice are impacting the global circulation. But at this time, I don't have any insight into that.
Yeah, I think, Rob, that's one area that's being researched right now, and that's more in the realm of climatology as opposed to meteorology. So, Linda, there probably is some sort of connection, but I believe there's work being done on that right now. So, I guess the straight answer is we're not completely sure yet. So, but a good question. Another one from John. This is more for Rodney's material. Are the EPO, PNA, NAO, and AO in phase with each other, or do they act independently? It's a good question.
Yeah, that's a great question. And so the short answer is that they are, I would say that they are independent of each other, although there are overlaps. And the reason why I say that is because all these teleconnections that we have, they are really our best attempts to describe phenomenon that occur over a large distance. And take for example the EPO, Eastern Pacific Oscillation. So you have the subtropical high pressure over Azores and subpolar low pressure over Iceland. And in a negative EPO phase, that's that favors a more wavier jet stream. And if you remember, if you can recall a positive PNA phase, Pacific North American pattern, is also associated with a wavier jet stream. So you have the ridge over the northern Rockies and the trough over eastern U.S. And so if you think of the jet stream as a continuum over the globe, it really, you can make a case that it is actually the same phenomenon. And the positive PNA may be associated with the negative EPO, but not always. So, so ideally, I guess, overall, I used to work for the climatology department in the Navy, and we kind of like to see teleconnections behave, but they don't always behave the way that you expect them to. So, and that is what makes climatology interesting, is when the things are not really in sync with each other. and and then you can kind of make a prediction, but then the weather pattern will unfold in a different way from what you expect. So I hope that gives more insight to your question.
Okay, thanks, Rodney. And Mike had asked a similar question and asked about how predictable the results of these interactions are. And I guess, Rodney, it's probably on the order of a couple of weeks, 10 days or so, 10 to 14 days for the most part. And we rely heavily on those model forecasts that Rodney had a couple of those diagrams there. So does that make sense, Rodney? Maybe like 10 to 14 days-ish? We kind of look at these?
Yeah, I think that sounds about right, Joe.
Yeah. Okay. I'm learning too, Rodney. All right. Question, let's see, from Kevin. Rodney, I think you mentioned this. Did the Arctic oscillation being in a negative phase affect temperatures in New England this winter? I believe it was mostly February, correct? When we had the cold, stormy outbreak?
Yes, Joe. Yeah, and also that cold stormy outbreak was actually, and I think we talked about this in a couple of our previous webinars. It was associated with the AO going from deeply negative towards neutral, and that week I think we had like storm systems every 3 days.
Okay. Yep. There you go, Kevin. From John, this one's I'll direct it to Rob. In which phase of MJO will rainy conditions occur near equatorial western South America, which just recently happened near Colombia? So I'm not sure if you know what phase we are in now, Rob, or what phase that occurs in.
Let me take a look. I did come prepared and decided to pull up the MJO because I thought Mike had asked that question. And I still believe we are in a La Nina, so it is still active. And right now it is actually located, so it looks like it's starting anew in the Indian Ocean right now. As far as the impacts it has, I believe the question was for Western South America. I'm actually
Correct,
not
yeah.
too informed. Yeah, not too informed on how it would impact the weather in that part of the world.
Would that be more of a phase 8 since it's more well out into the Pacific and kind of before things are starting over again? I'm not sure.
I'm not sure because I guess with South America being located up along the equator, the impacts that the MJO has for the United States really come from the moisture plumes that's going to have an impact on the jet stream, which obviously is going to impact South America. So I guess my guess would be, actually, I don't even want to guess.
So in other words, there may not be a direct connection then for what was going on over near Colombia with the MJO anyway. Might have been
right.
other things at play.
If you visit the Climate Prediction Center's website, they have a lot of great material on the MJO and all these composites that will actually show you the effects that it can have in all different parts of the world during different times of the year, because that's another thing that matters with these teleconnections is, the Arctic oscillation and the NAO, it's not always going to, produce colder conditions when they're negative. Sometimes it's more frequent to happen in the wintertime than summertime, and that can apply to the MJO as well.
Okay, and I'm not going to let you off the hook just yet, Rob. We have one from William. What force or forces drive El Nino and La Nina?
So the forcing comes from actually, it's driven by the Hadley cell, right, that we discussed on the first slide there. It's from the easterly trade winds. So when you have a strengthening of the easterly trade winds, it pushes warmer sea surface temperatures off the coast of South America westward, and then colder water has to come up from beneath, and that what's produces more high pressure near South America and lower pressure over Australia, and kind of generates that circulation. And then the reverse for El Nino is when you have a weakening of the easterly trade winds, so that you don't have any of that upwelling cold water, so you're really just left with typically warmer sea surface temperatures at the equator, where you're just going to get more tropical, showery thunderstorm activity. So it's the trade winds that really drive it.
All right. Question from Donna. Do all of these global weather patterns and oscillations fall under the Rossby waves category of study? So, I don't know, Rob, do you want to just address that?
Sure. I would say that all of the ones Rodney covered probably do, since a lot of the differences between the positive and negative phases of the PNA, NAO, AO, and EPO kind of determine whether you're going to have troughs or ridges in certain places. And maybe indirectly, you could say the MJO because it can have an impact on how it splits the jet stream with those moisture plumes. But I would say more the mid-latitude ones that Rodney discussed are definitely related to the Rossby wave trains.
Right. Okay. One from Kevin Rob, because you started off with this. Just maybe explain again how the three-cell model affects mid-latitude systems in the U.S.
So the Ferrel cell is kind of characterized by the mid-latitude westerlies. It's kind of when air sinks at the subtropics, some of it goes south towards the equator, and some of it goes, north and east towards the poles as it kind of spreads out from the subtropical high pressure. And with the pressure differences between the poles and the latitudes further to the south where it's warmer, you tend to get the stronger pressure gradient. So that's where kind of the jet stream comes from, and that's why it moves from west to east. So that's why the Ferrel cell, the mid-latitude westerlies, kind of controls our weather here in the United States. I mean, you don't really ever see storms moving from east to west in the United States unless it's from a tropical storm.
Okay. Rodney just had a technical glitch, so Rob, you're going to have to answer the next few. We just have a few more questions, and then we'll get on to our briefing, but I'll hand these off to you. From Mike, does any oscillation data predate the existence of satellite observations, or are they only a product of satellite observations? It's a good question.
So what's really interesting about teleconnections is that some really sharp scientists identified them early on. So from doing my thesis research in the NAO and PNA, I found that North Atlantic oscillation, they didn't know what it was mathematically way back in the 18th and 19th century, but they noticed it. They noticed that there were some winters in Europe that were just completely brutal, and other ones that were really mild. And later on, when scientists had the math and the technology to figure this out, they determined that that's probably what those folks were referring to was the North Atlantic oscillation. And a lot of this teleconnection research actually took place in probably the mid 1900s. I cited a lot of papers during my thesis research from the 50s and 40s. So I would think that predates satellites for the most part as far as weather goes. I'm not sure when the first weather satellite occurred, but was launched, but I think it was after 1950 for sure.
Yeah, it was the early 50s, was the old Tiros 1. All right. Let's see. We had a question about recommending a web page to keep up with these patterns for Robert, and I just put it in the chat. It's the Climate Prediction Center. You can go to their webpage. They have all of these different indices and the forecasts of them and what they mean. So if you want to find out more, you can certainly go to the Climate Prediction Center webpage. Let's see, from Wayne, can you expand on the relationship, if any, between the AO and the NAO?
Yeah, so there actually is, from what I have read, there is a pretty good correlation between the NAO and the AO. It's very rare that one's positive while the other one is negative. So if I were to say one precedes the other, it would probably be when the Arctic oscillation goes from positive to negative is when you'll probably see the NAO go from positive to negative. Not 100% sure on that, but just since the AO is kind of based on, I guess, for lack of better terms, the polar vortex, kind of the spinning around the poles. When it weakens and starts to drop colder air south, and you get more cold air intrusions, that links up with a negative NAO. So there is definitely a relationship there.
All right, and we have one more here from John. Just wants to know, is the Coriolis effect related to global weather patterns, or is it just an effect of the Earth's rotation?
So the Coriolis effect plays a role in pretty much all of meteorology. we went to school and how to take dynamics. I mean, it's one of the driving forces in the atmosphere. So I think the short answer is yes, it is going to be related to the large scale patterns as well, and it is also an effect of the Earth spinning. So short answer, yes. I mean, the Coriolis is usually involved in all large scale circulations.
All right, and I guess Rodney's
at least away from the equator.
okay. Thanks, Rob, for all those, and I think Rodney is back after his glitch. And just there was one question here from Benjamin. He wants to know, do you guys do webinars that people request, or do you plan them? We kind of do both. We have a number of kind of set topics, but a number of the ones, including this one, were recommended by folks like you. So, and in fact, the ones going into March as well, and in the future as we go into spring. So, please feel free to request a topic. Send me an email. We, love to keep these going, and the more topics we have to discuss, the longer we can do these. So, we also will have some event reviews mixed in. Yeah.
Can I jump back in for a second?
Of course. Go ahead, Rob.
So I was browsing the CPC website because I wanted to better answer the question about South America. And it turns out it looks like they're in phases 8, 1, and 2. There tends to be wetter conditions than normal for South America. So the answer to that question was yes, the MVO can impact precipitation patterns in South America. And it looks like it typically occurs from November to March is when it has the most effect.
Got it. All right. Gold star for you, Rob, for checking that out for John. Appreciate it.